Hello everyone, this is Electronic Communication Circuits Part 2 for Week 6. Make sure you're in the right video. If you have not watched Part 1, please go ahead and watch Part 1 first before you go to this video. Okay, so let's start with an exercise. If you have watched Part 1, you can do this. If not, go watch it. So given a maximum deviation of 21 kilohertz, so this is going to be our FD, we know this. Maximum modulating frequency FM 7, and carrier frequency of FC is 1 megahertz. It's asking what is the deviation ratio. We have talked about this, FD over FM, and then what is the maximum and minimum frequency. So max would be FC plus FD, and minimum would be FC minus FD, and then what is the number of sidebands that the bandwidth will occupy. Now this is going to be dependent on your modulation index. So if you were to solve this, so 21 divided by 7 would give you a modulation index of 3. So a modulation index of 3 would correspond to this guy over here in the table, whereby we have our carrier is negative, and then we would have 1, 2, 3, 4, 5, 6 sidebands. So N would be equal to 6 for MF equals to 3. Where is it? Yeah. So N equals to 3. We found out if our MF is 3, so sideband would be equal to 6, right? Okay, so what is the number of sidebands? So the number of sideband is equal to 6. And what is the bandwidth that it will occupy? So we will be using two equations. One is from the Bessel function and one is from the Carson rule. So for the Bessel function, bandwidth would be equal to 2FM times with N. So 2 times with 7 kilohertz times with 6. So that would give you 2 times 6, 12, 12 times 7, I don't know. So 2 times 7 times with 6 would give me 84 kilohertz, right? And for Carlson's rule, it is 2 times FM plus FD. If FM is 7 and FD is 21, that would be 28. 28 times 2 would be 56. Now this makes sense because Carlson is ignoring anything less than 2%, whereas Bessel is ignoring anything that is less than 1%, which means that Bessel will allocate more bandwidth for the smaller sidebands. Okay, so this is the difference, and both are correct. So here is another example that you can go through yourself. Okay, and then let's talk about noise suppression effects for FM signal. So remember that FM is supposed to have a constant amplitude, right? Only the frequency should be varying. But for noise in FM, this noise is actually a spike out of the normal amplitude. So this is how it looks like. So FM is very immune to noise actually because of this, because the noise actually extends beyond the constant amplitude, right? Which means that you can easily cut it off. So when you can cut it off, you will get your good FM signal again. So that is why FM is superior compared to AM in terms of noise suppression. So noise is interference caused by anything that produces transient signals. Transient meaning is very fluctuating, very random, unpredictable. So noise is typically narrow spikes of voltage, as we have seen just now, with very high frequency. So a frequency will look like this, right? But because it's very high frequency, it looks like a spike instead. So if sufficiently high, noise can destroy completely information signal. So FMS has superior noise immunity, clipping or flattening. We have this function. We can build this function to clip off, to keep everything at a constant amplitude. and therefore we can get our good FM signal again. So the demodulation process also suppresses noise and improves SNR. So imagine if you start with some SNR, let's say you start with SNR number of 5. After you have suppressed all the noise using the clipping method, it is possible to obtain an SNR that is greater than the input. That is how amazing FM is. So that's kind of counterintuitive, right? Because typically you would see output to become lower than input if there is no amplification involved. But in this case, because we clipped, we tried to remove anything unwanted from the beyond the amplitude, beyond the constant amplitude, we are seeing an improvement in the SNR. Okay, moving on to noise and phase shift. So how does noise introduce phase shift to FM? So let's talk about it. So a signal is always a vector. So signal is always a vector. I know you don't want to hear about vectors, but engineering involves a lot of vectors. So signal is a vector as well. So here we have a signal. It has some amplitude given by this arrow. The arrow denotes the amplitude and the angle denotes the phase shift. So here it's straight. So we can assume that the phase shift for this signal is 0 at this point. So when noise is added into the signal, so when we are adding vectors, we are actually adding the arrows, right? So this is going to be the angle of the noise component. It has its certain angle, and therefore when we add these two together, we can use the I don't remember the name. Well, basically you're trying to find the summation vector, which is from the initial point to the end point, and this is going to be your new amplitude. The length of the arrow is going to be your new amplitude. Okay, let me try to make this nicer. So if I were to write this mathematically, so signal when added with noise vector, it will give me a new resultant vector. So let's just call this R, and the new resultant vector is going to extend from the initial point up to the final point, and this is going to be your R. So the length of this arrow, or the length of R, is going to be your new amplitude of the signal or the output, and the angle that it makes with the initial signal is going to be the phase shift. Oh, so it's actually this guy, not this. Sorry, my bad. So it's actually phi. It's not theta. So phase shift is always referring to the original signal. So phase shift, because it's a shift, right? You shift from something. So the phase shift is with respect to the signal. Okay, so to find out the phase shift, we can actually find it through N over C, because this is just, what do you call this thing? Trigonometry. So it's opposite over it's not opposite over, it's opposite over adjacent. So this is my adjacent. So opposite over adjacent will give me the phase shift, or I can find out opposite over hypotenuse. This is what it's giving. So opposite over hypotenuse gives us the angle, yeah, when we use sine. But if we want to use what we have already here, which is signal and noise, so I will be using tangent. So it's going to be tangent N over S. Okay, so that is how you find out the phase shift with respect to the original signal after it has been added with noise. Typically, I don't actually give you the diagram, so I will give you values, right? So when we have values, this is going to be the equation that you will be using, which is phi, or phase noise, is equal to inverse sine. Is it called inverse? Inverse sine noise over signal. and you will get the phase shift in radians. And from this value, you will get delta, and delta is the frequency shift, not the phase shift, the frequency shift produced by the noise. So when you add the noise, you will get a phase shift. From the phase shift, you will get a frequency shift. So let's write that down. Phase shift, which is phi, and then you will get a frequency shift, which is delta. Okay, so delta can be calculated using this equation. So delta is phi times with the modulating frequency. So this needs to be in radians, so make sure you know how to use your calculator in radians. And modulating signal frequency is in hertz to get your frequency shift. Okay, so this is an example of noise and phase shift. Assume that you have an SNR of 3 to 1. So SNR is actually S over N, signal over noise, and it's telling you that the signal is 3 times stronger than the noise. So if we have SNR, which means that we can actually find out what is our phi or what is our phase shift, right? So if S over N is 3, therefore N over S is just 1 over 3. So you can actually plug it here. So 1 over 3 of this in radians would actually give me a value of 1 over 3. Convenient. So from 1 over 3 radians, I plug into this equation to find out what the frequency shift is when noise is added to the signal. So when noise is added to the signal, I would get 1 over 3 times with the modulating frequency, which is 800 hertz, and that would give me some value of 271. I'm looking at the answer down there, 271.8 hertz. Okay, so the next question is, so the noise is introducing a frequency shift from the original frequency by 271.8 hertz. Okay, so assume that the maximum allowed frequency deviation is 5 kilohertz. This noise is introducing 271, but the maximum allowed is 5 kilohertz, which is quite a lot. So this is 5000 hertz. Find the ratio of the frequency shift found above to be the maximum allowed. Okay, so here the equation for that would be frequency deviation over maximum allowed deviation. So delta over delta max. So delta max is just basically FD by max. So this is also the same as this guy. Okay, so don't get confused. It's the same thing. So delta is 271 introduced by the noise. The delta max or the FD max is 5000. So what you're going to get is 0. What would that be? What would that be? Let me write that. Okay. So that would be 271 over 5000. That's going to give me something 0.0544. Okay, so since it's frequency over frequency, it's unitless, and now it's telling me the reciprocal of this value gives you the output FM SNR. Just now we started off with an input of 3 to 1 SNR. Now it's telling us that whatever that 1 over d max, d delta over d max is going to give you the output SNR. So just 1 over 0.0544, you would get an SNR of 18.4. So introducing the noise actually improved the signal, which is quite weird, right? But it happens. Okay? Sorry about this. So I did not manage to edit this slide. I don't know why it's presented this way. Let's just talk about it. So these are the advantages and disadvantages of FM signal. So the advantages is that noise immunity. We've seen that even if we added noise, sometimes the SNR improved, which is weird, but that's good for us. And if we have noise spikes, we can actually clip it off and we will get our original FM signal again. So that is amazing. And then it also has capture effect, the difference, as it is able to capture the difference as low as 1 dB, which means that it's very precise, or it has a high resolution. It sees everything, it does not lose information. That is what it means. And therefore, it has good transmitter efficiency. However, the disadvantage of FM signal is actually that it uses too much spectrum space. We have seen this. We have seen the Bessel function table. We have seen so many sidebands, and maybe some of you are traumatized by it, but don't be. It's just a table. But FM signal uses a lot of spectrum space compared to AM, and that is the disadvantage. So we have to allocate more bandwidth. However, we can reduce this by reducing the modulation index. So we can control it by controlling the modulation index, but we'll have less noise immunity. So the higher the modulation index, the better your noise immunity. The lower your modulation index, we will be less immune to noise. And then FM signal is commonly used in those where adequate bandwidth is available. You need a lot of bandwidth for FM signal to be transmitted efficiently. Okay, so that is it for this part. I couldn't continue with part 1 because I was too tired. So bye bye for now. So I'll see you for part 3 later. Take care. Bye everyone.